Hi everyone, welcome back to our group channel. My name is Zeng, a PhD student of Transport Lab in University of Sydney. Today I'm going to share my video abstract of our recent publication on measurement. A dynamic, confident, three-dimensional multi-object tracking method based on spatio-temporal association. Together with my supervisor, Professor Ramezani, we're trying to improve LiDAR-based multi-object tracking, making it more accurate, more robust, and faster, especially in complex driving environments. So let's start with the basics, multi-object tracking, or let's call it MOT. This is the process of detecting and following multiple objects across video frames. So with a fixed camera, MOT is usually done using two-dimensional images. It works well in good lighting and with rich textures, but when the scene is dark or objects are far away, performance drops sharply. So that's why researchers start looking for other sensing solutions. LiDAR, as a short for light detection and ranging, uses laser pulses to create precise three-dimensional maps of the surroundings. So unlike cameras, it's not affected by lighting, and it provides accurate distance measurements. That means better object localization and shape estimation, even in the dark. When LiDAR is fixed, MOT becomes more stable because objects are tracked in a three-dimensional space. But in autonomous driving, both the sensor and objects are moving. This creates new challenges like handling changing perspectives, noise, and temporary occlusions. In self-driving cars, perception systems are the foundation of decision-making. MOT can be camera-based, LiDAR-based, or a combination of both. In our work, we focus purely on LiDAR-based tracking to take full advantage of its spatial precision and robustness to lighting changes. But LiDAR or purely LiDAR MOT isn't perfect. It faces four big challenges. The first one is limited information in sparse point clouds without any texture or color information. The second one is complex and dynamic scenes. The third one is difficulty maintaining continuous tracking when objects disappear temporarily, and also relatively low efficiency compared with camera MOT. So our work is designed to tackle all four at once. We take Kitty dataset for example for our experiment. So this frame shows the framework of our work. We combine motion prediction, spatio-temporal association, and a dynamic confident mechanism to maintain object IDs, even when detections are noise or missing. Here is what LiDAR detection looks like. These bounding boxes come from detector and are saved in a text file before entering our tracking pipeline. So we use a constant moving and turning acceleration model for prediction. It assumes accelerations remain constant over short-term intervals, making the prediction stable even during short-term occlusions. One of the key innovations in our method is what we call dynamic prediction confidence. Here's the idea, when the tracker predicts where an object will be, the prediction has a confidence value. So if in the next frame the prediction finds a matching detection, the confidence stays high. But if no match is found, like the object is temporarily occluded, the confidence drops slightly. But why is important? When confidence is high, the matching process is stricter, so we avoid mismatches. But as confidence gradually decreases during occlusion, we allow a wider matching range. This makes it easier to reconnect the same object when it reappears, even if its position or appearance has changed a bit. So in short, dynamic confidence help balance precision and flexibility. So here you can see how we merge the different matching scores, geometry, velocity, feature similarity, and distribution similarity into a joint score matrix. So dynamic confidence is directly integrated here. So the matching process adapts over time, depending on how reliable each prediction is. When comparing with a baseline method like FanTrack as it shows on the right hand of the video, our tracker shows smoother and more stable trajectories, especially in a temporarily disappearing object. So all experiments run on a desktop with an AMD CPU and the NVIDIA GPU. Importantly, our method can run in real time on CPU alone, almost 300 frames per second, making it lightweight and deployable. Let's see what this means in action. Imagine a vehicle moving along the road. At time t, it gets completely blocked by any other object and disappears from the LiDAR's view. In a standard tracker, after a few missing frames, that vehicle might be considered gone, and when it reappears, it gets a brand new ID. Our method works differently. Thanks to dynamic confidence and survival time management, the tracker remembers that object during its absence. So the confidence decreases slowly, allowing more relaxed matching when the object comes back. Here's another case where a vehicle is fully occluded and reappears later. Our dynamic confidence strategy successfully reconnects to its original ID, maintaining the continuity of the tracking sequence. And let's get some takeaways. In short, our method combines accuracy, stability, and efficiency. It's robust to occlusion, works in real time, and achieves state-of-the-art results on benchmark datasets. We are a control group of Transport Lab in University of Sydney. We're driving smarter cities and better lives. If you like this video, remember to like, comment, and subscribe our channel for more.